We're ready to complete our list of fundamental postulates of the theory of quantum mechanics. The first one, collectively, is that everything can be described by some element of a Hilbert space, which is a fairly abstract thing. So the second postulate is all about how we get numbers out of that. Whenever we actually make a measurement on a state, then the system jumps, the state jumps to a particular value with a particular probability. And the choice of those values and probabilities are governed by the choice of measurement and the measurement postulate. And whenever that's not happening, our state still evolves. It evolves according to a first-order differential equation. And the operator that describes that linear evolution is another observable called the Hamiltonian, which is the observable for energy. And this equation is called Schrödinger's equation, after the famous Austrian physicist Erwin equation. Because the Schrödinger equation is a first-order linear equation, it has very simple solutions in some sense. Quantum mechanics is actually very hard because the vector spaces can be extremely large. As you add more and more elements of physical systems together, the size of the Hilbert space grows exponentially. And so it's a very large system, but it's a linear system. And linear systems, we have very powerful tools for solving them and finding the time evolution, and they come down to looking at the eigenstates of the Hamiltonian. Let's try and solve Schrödinger's equation, assuming that we know the eigenstates of the Hamiltonian, in this case labeled by n. Let's assume, first of all, that we're starting in one of those eigenstates. So what is the state as a function of time going to be? Okay, we examine that, and in fact, if we apply the Hamiltonian to this state, we're just going to get the energy eigenvalue popping out, E of j popping out. And that equation then is one of the very few differential equations that we actually know the answer to. So even if you didn't spot that that was the answer, you can look at that now, and you can see that trivially for t equals 0, it's got the right solution. And you can easily show that if you plug this into this equation here, that you get the right answer. In other words, it satisfies Schrödinger's equation. And because this is a linear first-order equation, if you've got the right initial condition and you satisfy the equation, you know that the solution is unique. And so this is definitely the solution. So that's what we get if we start in an eigenstate. So an eigenstate doesn't change, it stays an eigenstate, it's just the phase that's changing. That's why they're called stationary states, because you don't change from that state. But in general, of course, we don't start in a particular eigenstate of the energy, we start in an arbitrary state. And an arbitrary state can be written as an arbitrary superposition of those eigenstates. Now, because the evolution is linear, because we know how each of these evolve, we actually know how this thing's going to evolve immediately. So we look at that, and again, we can show very trivially that when t equals 0, that goes away, so we've got the right initial state. And again, if we take this solution and we plug it into here, then we show that it solves the Schrödinger equation. And so this is definitely the solution. And this is why we were so keen on finding the eigenstates of the Hamiltonian, because once you know the eigenstates of the Hamiltonian and you can express your initial state in terms of those eigenstates, then you've essentially solved the dynamical quantum system.